this is how.
This is the video for light as an electromagnetic wave, and where we measure the speed of light, which is very cool, very interesting. So you should have already talked about waves before and about sound waves specifically, and that they travel through something, they travel through different media. And the fact that they're traveling means that they have a speed, they have a velocity at which they're traveling. So the speed of sound on Earth in air is like 320 meters per second, I think. But what we're going to prove today, so that you might be like, is light a wave? Does that make sense? No, that seems crazy. But when you turn on the light, it seems instantaneous to us that everything is just lit up, but actually it's not. The light is traveling from the light bulb to all the walls, to you, to your eyes and everything. And we're going to show that we can calculate that speed and prove that light is actually a wave. So the most important formula for this is V is equal to lambda F. And in this, V is equal to the speed, this goes for all waves, the speed of the wave. Lambda is equal to the wavelength, which we'll talk about in a second. And F is equal to the frequency of the wave, So lambda, the wavelength, is a distance, which we measure in meters in this case. Frequency is a bit complicated. It's measured in time, but it's how often something occurs. So it's per second. So it's second to the -1, or hertz, named after the scientist Hertz, who kind of figured this equation out, I believe. So the speed of a wave is how far something travels in a certain time. So this is meters per second. So it's distance over time. That's not very helpful either. It's a bit complicated, but we don't have to talk about that bit. We can just know that this is our unit. We need it in meters and we need it in seconds. So we'll talk about the wavelength and the frequency. If we have a wave like this, the frequency is how often in time we get from each of these points. How frequently that happens, frequency. And then the wavelength is the form of which, this is very good, the form of which where the wave repeats itself. So you can see the wave is going down and then it goes back up, and here it's going down and back up. So this distance here is one wavelength. So if you had, the wavelength is always just measured like that, but like a high frequency is like this. So this is the wavelength, and let's say this is time. But the distance in the one is measured in distance, one's measured in time. And then a big, long frequency is like this. So it's a lot much slower. It's generally less. Okay, so now we're going to talk about light as a wave. What we're trying to determine, we had V is equal to hf, but the speed of light is denoted as c, and we know what this number is. It's 3 by 10 to the 8, complicated. It's 3 with 8 zeros. So we have 1, 2, 3, 4, 5, 6, 7, 8. And as we said before, everything here we're going to measure is going to be in meters per second. So this is the answer we are trying to find. Very important. So we have that it's in meters per second. So this is the speed. So we have C is equal to lambda F. So how are we going to find lambda and how are we going to find F? The easiest part is, so what the experiment that we're doing is putting out chocolate in a microwave, and the frequency, we'll explain how that works in a second, but the frequency of the microwave, of the microwaves inside the microwave oven, will be given on the back. I think for our microwave it was 2450 megahertz. Mega indicates that it is 10 to the 6. You can look this up, but we'll have this in the notes. Most microwaves are about 2500 megahertz anyway. So you have 2450 by 10 to the 6, which means you add 6 zeros. So you have 1, 2, 3, 4, 5, 6. So that's a very big number, and this is hertz, which is per second. So this is now in the correct unit, which is all we need. So now we want to find out what lambda, so we have C, well we know what C is and we know what we're looking for. We have F, so we just need to find lambda. And lambda is going to be part of the experiment, okay? So we're going to put the microwave in the oven. We're going to take the spinning thing out. I'm going to explain that part in a separate video. The wave is going to travel over the chocolate. And here are the melting points, the parts we're going to measure. How that works is when you add two waves together of the same frequency, they literally add up. You can just add them together. So if you have this added with this, you get this. You get double the amplitude, same frequency, everything like that. If you have this and this, which are opposites, you get this. So when you add up certain, like two waves that are the same, you get this repeated. You get super high peaks and super low peaks. So these low peaks are going to be areas that don't melt, which is going to be most of here, or like anywhere here really, is parts that aren't going to melt too much. But then we have a few super high peaks that are going to melt, if that makes sense. What else? So we just need to find the distance between these two peaks. But as you can see, these peaks are not a full wavelength. These are only half a wavelength. So whatever we find this distance, we'll call it A, which is going to be, sorry, I'll redraw this. This is our chocolate bar that's going to melt. This is, so just had the chocolate in the microwave, not spinning. So it was staying completely still on the plate. I had to take all these bits out of the microwave. And I had it in for literally about like a minute, less than a minute on medium low, so the lowest it would go. And you can see here we have two melting points and everywhere else is still solid, but here and here are definitely melty. So we're going to measure it from center to center-ish, and that's about 7 centimeters for this. Now, you just need to check the wattage frequency, the frequency of your microwave as well, which should be written somewhere on the back. Okay, so I'm just going to write what we have so far. After measuring the chocolate bar, we have that our lambda, which is equal to 2a, which is equal to 2 by, what would you say, 6.5 centimeters. Lambda is equal to 13 cm. Cent is by 10 to the minus 2. But the kids should know how to do the decimals for centimeters to meters because it's taught quite early. So you have 0.13 meters. So this is in the correct unit. We also had that our frequency was 245012345 per second, which is perfect. We have everything in the correct unit. So now all we need to do is plug it into our equation. Our equation being C is equal to lambda times F. C is equal to 0.13 multiplied by 450000000. Obviously this is a really hard calculation. Kids don't really, I wouldn't know how to multiply a decimal off the top of my head, so you can just chuck it into a calculator, which I have done already. So you get that the answer is, let me see, the answer to this is 318,500,000 meters per second. Perfect. So what was the answer we were looking for? It was 3 by 10 to the 8, which is 3 with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8 was our ideal answer. We have 1, 2, 3, 4, 5, 6, 7, 8. So we did get that RC was approximately, so 3.1 by 10 to the 8, which is really good and really close. So the fact that we got a very close answer, we weren't being that exact. Obviously we used a ruler. We should have, the melting points ended up being quite large and things like that. If you want to make sure to get somewhere near here, you should be getting about between 6 and 7 centimeters for the distance between the two melting points. And most microwaves will be about 2,500, 2,450 megahertz. So you can calculate what the exact distance is meant to be, but it should be somewhere between 6 and 7 centimeters, and that should work out pretty well. Thank you for watching. I hope this is clear. I feel like it is a bit complicated, but I'm going to put up a lot of visuals about waves, so that should help.
Created using Powtoon.